back to tonight's lecture. Dr. Carolin Villforth is a senior lecturer in the Astrophysics group at the University of Bath, and a position she's come to via Heidelberg, Finland, La Palma in the Canaries, Florida, and St. Andrews, and probably a couple of other places as well. So we're very glad that she's fetched up here. Let me hand over to Carolin.
Yeah, thank you, and good evening. So today I'm going to talk about supermassive black holes, and by the end of the evening, I hope I will have convinced you that supermassive black holes basically exist in all galaxies, including our own, and that we have to actually work quite hard to feed material into them, but that amazing things happen when we do feed them, and that we can in fact affect galaxy evolution as a whole. But before we can get started with supermassive black hole and all that exciting physics, I want to start with kind of the astronomy we might all know from school, and that is basically what we might see on a clear night when we look up into the skies. And this is a picture of the night sky. And what you see there is basically kind of the stream of stars. And this is, of course, the Milky Way, our own galaxy in which we sit. And what we see there, all these little dots, are basically stars. They're stars very much like the sun. Some of them are less massive, some of them are more massive, but basically everything we see by eye are individual stars. These stars, of course, make up galaxies. So this is one of the kind of beautiful galaxies you might have seen. So what we see here is just a large assembly of stars. This is something quite close to our own Milky Way that we live in. And you just see a distribution of stars here rotating around the center. You also see this kind of grayish lanes across, and that's kind of gas and dust kind of mixed in. And that's a galaxy, right? That's a galaxy. It's made out of stars. And galaxies do not live in isolation. So galaxies live in groups of galaxies. They have neighbors. And while in most cases, they will just basically orbit around a common center of mass, in some cases, what we get is interactions of galaxies. And in this case, what we get is these galaxies kind of flying past each other, and they're going to basically slow down and eventually merge into a single galaxy. And during those interactions, you see these very beautiful structures. You see these basically ripped out arms here, and that's basically gas that's stripped off the galaxy as it's interacting. So those are galaxy interactions, and they happen because galaxies have neighbors and they live in groups. We also have galaxies that look nothing like the beautiful galaxies we often see. So most of the time when astronomers show you galaxies, they're the ones we've seen before. They're kind of beautiful, they have structure, they're amazing looking. While in fact, quite a lot of galaxies look like this. So what you see here is what we'd call an elliptical galaxy. You see that this looks very, very different from the galaxies we've seen before. We no longer see these kind of dusty, wispy arms that we saw in the one before. And we see it also doesn't have structure, it doesn't have arms, it doesn't have changes in color. And this is because what we have here is basically a dead galaxy. All the stars are formed, and it doesn't have new material. It's just a collection of relatively old stars. And this is elliptical galaxy, which is a kind of galaxy astronomers hide from the public because they're not very pretty. They're cool though. Right. And basically up to about the 1960s or so, this is what astronomers knew was in the sky, right? This is what we thought was out there. There were stars, there were galaxies, they were living in groups and so on. But supermassive black hole, which I'm talking about this evening, are actually quite new. And I'm going to show you now a video that shows us the signature of a supermassive black hole in our own galaxy. So I hope that this should start the video. Just going to wait a second. If not, I have to press again. Okay, but while I do that, I could just say that what we're going to see is we're going to start again with a picture of the Milky Way, which is what we have here. And I think I have to press play to, yeah. And what we're going to see here is basically a zoom in into the center of the Milky Way. So we're going to end up with this pretty picture here, but this video moves in kind of surprising speeds. Yeah, so this is basically the center of the Milky Way. This is what we're going to end up at the end of all of this. Why is this not doing what I thought it was? No. No, now it's doing it. Sorry. Right. So we're zooming in now into the center of the Milky Way. So we're flying here to the very, very center of the galaxies we sit in. Remember, we're kind of a disk and we're in one of the outskirts arms, and we're now zooming in. And this is somewhat dizzying because you start to see how much detail we're missing if we're just looking up. So all of this is real, right? We keep zooming in and we keep seeing new and new stars. And once we've zoomed in to the very, very center, if we observe this and monitor this over about 10, 20 years, what we see is this whizzing little stars kind of whizzing around one position. And this is now computer animation showing that. So what you're seeing is that we can monitor the stars at the center of the Milky Way, and they're just orbiting a single location, which is shown here. And because we know Kepler's law, which tells us basically the mass of a single object, if we know the orbits, we can determine the mass of this. And we can determine that the mass of this object that everything is orbiting around at the center of the Milky Way is about 1 million times the mass of the sun. Now, 1 million times the mass of the sun is a lot. It is a lot more than any stars that we know. And we also see that it's entirely dark. So what this tells us is that what we have there in the very, very center of the Milky Way is what we call a black hole. A black hole is a mass so dense and compact that it's entirely collapsed. It emits no light. It's extremely, extremely compact. And we see those stars orbiting. And we can measure the mass of it. And it's about, as I said, a few million solar masses. And that is what we call a supermassive black hole. And you see that this orbit here is all very, very compact there, right? So this is an observation that was made in the late 90s, early 2000s. This is actually so exciting that, where did my Nobel Prize winners go? I had the Nobel Prize winners here. I'm going to tell you this now and you can look up the pictures. So this discovery of the supermassive black hole in the center of the Milky Way was so exciting that the Nobel Prize in 2020 for physics went to Andrea Ghez and Reinhard Genzel for making this discovery, and for Robert Penrose for doing the theoretical predictions. Okay, so there's a supermassive black hole in the center of the Milky Way, which is exciting. But what astronomers also learned over the last decades is that not only is there a supermassive black hole at the center of our own galaxy, there is a supermassive black hole in basically every single galaxy. So every single galaxy that we see, every one that you see in here, at the very, very center, there's a supermassive black hole like that. Which is extremely common. And now we can ask ourselves, well, what is the contribution to the mass of the galaxy, right? 1 million solar masses sounds like a lot, right? But what we have to keep in mind that galaxies overall are extremely massive. So despite the fact that the supermassive black holes will be extremely massive, the majority of the mass, even ignoring the dark matter, is in the gas in the stars. So overall, the supermassive black hole is a tiny, tiny contribution. And the black hole masses for these supermassive black holes can range from millions to billions solar masses, so they're really quite heavy. But despite that, again, tiny fraction of the galaxies. And what we've learned is that basically, irrespective of the galaxy mass, the supermassive black hole contains some fixed fraction. So it seems to be always the same fraction as in the black hole, which is actually quite an interesting discovery. So that's their contribution, right? Ah, no, they went there. Okay, but back to that. Those are right at Genzel and I guess they did these observations were like extremely, extremely challenging. And I got the Nobel Prize in physics for that. So fantastic for them. So what we can now do is we can ask, well, these supermassive black holes are everywhere. We can ask, well, do they matter for the galaxy? So are they just weird curiosities that are sitting in the center of the galaxy and that basically don't matter for the galaxy at all? We could forget about them. We could understand galaxies all the same. This is a sensible question to ask. So our first question could be, well, does the black hole matter in terms of the gravity? So kind of gravity holds galaxies together. So does the supermassive black hole contribute to that? Does it matter for the gravitational composition of the galaxy. Well, we can think about the kind of size of the system. So the galaxy size will be something like tens of thousands of light years, right? And again, most of the mass is in the stars and the gas. The black hole, again, millions to billions solar masses. Black hole size is very, very small, much smaller than a light year. So the one thing we can basically calculate as physicists, we can try to figure out, well, what area of the galaxy is actually basically dominated by the gravitational influence of the black hole. So we call that a sphere of influence. So basically, if you are a star orbiting in the galaxy, do you really feel the black hole, or are you mostly influenced by all the other material in the galaxy? And we call that the sphere of influence. And it turns out that that area is so tiny that if I put a dot on there, you wouldn't see it, right? So basically, the black hole really, really only dominates the galaxy in terms of its gravitational influence in the very, very center. So this might seem a bit confusing because basically, despite the fact that the black hole is individually so massive, it doesn't really matter for the gravity overall because there's so much more stars and gas. So basically, does the black hole matter for gravity? The answer is kind of no, unless you're in the very, very center. So that's the center we saw earlier for that video where we saw the stars go around. Unless you're in that very, very center, so there's like 10 or 100 light years, so it depends on the properties of the galaxy doesn't really feel the black hole. You can't really determine that it's actually there. Okay, so that's, I guess, disappointing or something. But I mean, I came here to tell you about the influence of black holes on galaxies. So if it doesn't matter for the gravity, why am I standing here and talking to you about this? And the kind of answer to this, it might be sometimes a bit counterintuitive. Because oddly, what really matters, why the black hole really matters, is not its gravitational influence, but the emission from near the black hole. So I said before that the black hole is basically so compact that no light can escape. So the black hole itself does not emit light because the light just cannot get out. But it turns out that if you throw some gas at the black hole, what happens is that it will form something like an accretion disk, which we see here. So we see here the black hole in the center. We see some chats coming out. We'll talk about this later. And we see this kind of swirl going inwards. So basically, the gas will arrange itself and it will kind of just spiral and spiral inwards. And as it does that, there will basically be friction between those different rings, and it will heat up to very, very high temperatures. If you heat something up to very high temperatures, it starts glowing, it starts emitting light. And it turns out that this is actually what matters for the black holes. It's the emission from accretion onto the black hole. Okay, and now I'm going to do the most kind of physics lecturer thing, and I'm going to show a plot. And if you really hate physics, you can just like fall asleep for 3 minutes. So what? No, they can't see the top thing. Can I move that thing? It's kind of, there's a label to these axes. Can I move that thing? No. No. Okay, then I'm going to tell you what it says. So on that top line here, it says distance from black hole. So what we have here is a graph. There's a supermassive black hole. There's a distance from the black hole. Right, so it goes further and further away. And I think it's fine. It's just... Of it, we'll just leave it. It says distance from the black hole. And what I've basically plotted here with that red line is the potential energy of mass orbiting the black hole. Now, what does that mean? So that basically means that if there's material orbiting, like there's planet orbiting the sun, it has what we call a potential energy. Now, energy is conserved. So one way of thinking about this, if you want to leave Earth, you have to expend energy to basically climb up that hill and leave Earth. Right? It's the same if you wanted to leave the solar system, you'd have a kind of a low potential energy here, so you have to expend energy to basically get up there. So that's how potential energy works. But it also works the other way. So what we have for a supermassive black hole is we basically have material kind of sliding down this red curve here, this potential energy curve. And as I said before, basically we have to conserve energy. So basically as it's falling down, we have to somehow release this energy. How do we release this energy? We release this energy by heating that disk and by emitting radiation. So basically light goes away. So if I now think about this, basically I could say, well, if I'm at the outskirts of this and I basically take a step, I basically release some energy so I can fall into the black hole. And as this gets steeper and steeper, this basically gets a steeper and steeper slope. So if I take a step, a lot of energy is basically radiated away. So as I fall into the black hole, I have to release energy and it's radiated away. Okay, that's fine. But the same is true for Earth or the sun or really anything that has mass. Oh, that goes away. Oh, no, that is the wrong way around. Right. So now what we have to think about is the fact that the black hole is really, really compact. So if we think about a star or non-black hole, basically the surface would be somehow far out on that curve. So maybe I release a little energy as I'm falling in. But what I don't have access to is this really, really steep part of the gravitational potential where lots of energy is radiated away. And this is really the fact that causes this kind of accretion of material onto the black holes to release so much radiation. And this is why it's that radiation release that really matters for galaxy evolution. So I had to copy this from my computer and I had a cool fire effect, but it's gone. So basically, that was a fire effect here. So basically what that means is that if I throw some material in the black hole, it has a certain kind of rest mass, and that rest mass is energy. And if I throw something into a black hole, 10% of that rest mass gets released as radiation through this process that I just described. And that is absolutely amazing. Because if we think of fusion, which is something we would love to have on Earth to solve all of our energy problems, that's kind of below 1%. So this is like more than an order of magnitude better. It is extremely, extremely efficient at creating radiation. And that is because we can get to this, because the objects are so compact. So counterintuitively, despite of the fact that we know black holes for not emitting any light, it's material falling into it that really can kind of dominate emission in a galaxy. So does the black hole matter for emission in the galaxy? Yes, it does. It really, really does. And the way we can look at this is we can look at something like this object here. And what this object here is an accreting supermassive black hole. It's called 3C273, but that doesn't really matter for this. So what we see here, right? You see what we'd call a point source as astronomers. You see kind of the diffraction spikes here. This is an accreting supermassive black hole. There's a galaxy somewhere there, but because the black hole is accreting, it outshines the entire galaxy. And again, we're still in the situation where the black hole contributes less than 1% to the overall mass of this galaxy. But once you throw material into it, it can outshine the entire thing by a factor of 100 or so. And that is absolutely amazing, right? So the black holes can really matter now. They dominate the galaxy all of a sudden. Okay, so that's cool, that's exciting. I showed you earlier the black hole at the center of the Milky Way. The black hole at the center of the Milky Way is not active. So it's not kind of, material is not falling into it. It doesn't have one of those shiny disks. Overall, accreting supermassive black holes are quite rare. Only about 1% of galaxies have an actively accreting supermassive black hole. So basically, most of the time, the supermassive black hole will just sit here the way it does in the Milky Way, not do anything. And then every now and then it's getting this active states where we accrete gas. And at that point, it can dominate the galaxy. That's another galaxy with an accreting supermassive black hole. You might also recognize that this is quite kind of asymmetric. So this is actually also a galaxy merge. So now we can ask, well, this is great and all. So how can we feed a black hole? Because this seems like a really interesting process, right? How can we make sure that we get gas to the black hole so it can kind of start this accretion and outshine the galaxy? But for this, we have to go back to what I said before about the gravitational potential and where the black hole really dominates. So I've now drawn another galaxy. So again, we have a size here of about 10,000 light years or something. And again, we kind of have that the black hole only dominates the gravitational potential in this very, very center. And if I drew this actual dot to scale, again, it would be much, much smaller. So what that means is that if I, as the black hole in the center of the galaxies, would like to accrete some gas, there isn't much very close to it, right? There isn't very much gas around because it's a tiny, tiny area. But there's all this reservoir of gas around it. So ideally, what I'd want is I would want some kind of gas to be moved inward towards the black hole so it can start this accretion process, shine bright. But, I mean, fortunately or unfortunately, galaxies are really quite stable. So what we see here is kind of a disk galaxy. This galaxy is rotating, right? So this is rotating. So all the material in there is basically on stable orbit. So it doesn't just fall to the center, right? So if there's a galaxy like that, none of the gas will have any reason to basically fall towards the center of the galaxy and start feeding it. So how do we feed such a black hole? And this is actually one of the main puzzles in the field still, like how do we really need to make this happen? And one way we could do this is something that I mentioned earlier, is basically, right, we say this galaxy is stable now, we just disrupt it, right? If you disrupt it a bit, some gas might get disturbed from its normal orbits and fall towards the center. So what I'm going to show you next is a simulation of a galaxy merger. So previously we looked at these kind of mergers of galaxies, and I said that they really kind of disrupt the galaxies. There's a lot of forces on the galaxies. So we're going to see So what we're going to see here is a simulation. This is not reality. And we see two galaxies coming in from two sides. There's a time scale up there, but it doesn't really matter that much. And we start to see kind of what happens as this goes on. And what you see that the galaxies came in and they were kind of quite stable. And as they passed through, some of the material was stripped out. So what happens at that point is basically some of the material gets ripped out. The other thing you might see is that the centers start to be a lot more compact. So basically what you have here is that as some of the material is flung out, other parts of the material become much, much more compact. And so what you have is an inflow of gas to the center of a galaxy. And what that means is that if you have these kind of galaxy collisions, you no longer have a stable galaxy. You have a disrupted galaxy. The orbits of the gas and the stars are disrupted. And what we can show with these kind of simulations and also in reality is that when that happens, a lot of gas comes to the center of the galaxy. And as a lot of gas comes to the center of the galaxies, you have much, much higher densities of the gas, and the black hole can start accreting. So this is one of the ways we can feed a black hole. There are other ways to feed a black hole. If you have bars in galaxies, you can drive gas inwards. But basically what you have to do is you have to kind of push gas towards the center by disrupting orbits. And when that happens, we can then have an active black hole. Okay. So if we've come that far, we can say, well, okay, so now we figured out that there's a supermassive black hole in the center. We figured out that there's ways we can move gas to the center to start accretion onto the black hole. And now we can ask, well, now when that happens, so we saw from the pictures that accretion disk, accreting supermassive black hole, can really outshine the entire galaxy. But we can also ask, well, does it really matter? So it's really, really bright, sure. But does the galaxy feel any effect of it? So if I basically turn on accretion onto a supermassive black hole, does anything in the galaxy change in the future, or does it just stay the same? And for that, we kind of have to think about what a galaxy is made of. So we're going to go back and say, what's the galaxy made of? And what I show here is kind of a multi-wavelength image of the same galaxy. So all the little images you see are the same galaxy. But you might notice that they look very, very different. So if you see the upper right, the orangey bit here, you can see, first of all, that you don't really see the center at all, right? And you see really, really nice arms and rings around it. And what that is kind of far infrared. So that is kind of the cold gas and dust that can form new stars. So basically, if I want to form new stars in the galaxy, what I need is rather cool material, because if I heat something up, it expands. And to make new stars, I want it to collapse. So it needs to be cold. So what I see in orange here is that's basically all the gas that can form new stars, potentially. So that's great, right? On the upper left, that's kind of the bluish image here. What I see is existing stars. You see the center is a bit redder, that's because the stars are older, and you see this kind of blue fluffy stuff around it, right? And what that is, that's the existing stars. That's the stars in the galaxy that have already been formed. And they form this nice kind of disk here. Okay, so we have existing stars in the galaxy, and we have gas, and also dust. So it's basically dust is when something gets quite cold, you can basically start to form dust. That's also good for star formation. Gas and dust in the orange here. So that's what my galaxy is made of. So what we can think about now is, well, if you still can't see the writing, but basically the way galaxies work is they form new stars from cold gas and dust. So that is kind of the orange stuff I saw before. In this image here, the one we saw before, you see these little kind of wispy arms, the kind of grayish, reddish kind of things in arms. That's the gas and dust that we see, it's blocking the light. So basically, and if I have this kind of cold gas and dust present, I can make new stars. It's great. On the other side, we're going back to this galaxy we saw before. If I have a galaxy that contains little cold gas and dust, I cannot form new stars because there's just nothing there to make new stars. So that's the basic facts of galaxies. Okay, so now we learned what galaxies are made of. We can then think again. It's like now that we know what's in the galaxy, what effect does the radiation released from accretion onto the black hole have on the galaxy? Let's go back to this question. And but now we go to cartoons, and on the top layer, which is covered here, says like, what effect does the black hole, or what does the black hole do to? So our questions are, what does the black hole do to the stars in the galaxy? So the ones that already exist, they're already there, or they were formed. To any kind of gas clouds or cold gas clouds in the galaxy. Basically, if I have the accreting supermassive black hole in the center, the radiation comes out. What does it do to those components of the galaxy? The first is the boring one. What does it do to the stars? It does nothing to the stars. So basically, if I turn on the black hole in the center, it starts radiating. The stars, basically, they're so rare. So basically, most of the volume is not stars. They might absorb a bit of the light, but it has no effect on them, right? They emit their own light. They don't care. So the stars in the galaxies are not really affected if the black hole accretes. They just stay the same. It doesn't have any kind of opportunity to push about. Nothing happens. Stars stay the same. But what happens to cold gas in the galaxy? Well, if I have cold gas in the galaxies, what I've just done is I turned on a really bright light in the center of the galaxy. So what that means is that if there's some kind of cold gas cloud, it will, of course, absorb that radiation, right? There will be radiation coming towards it, and it will increase the temperature. That's the same way if you build a snowman or so, and you leave it out in the sun, or it gets sunny, right? It absorbs the radiation from the sun and it starts to melt because it absorbs the energy and it gets warmer. So if I have cold gas in the galaxy, if I go back to my little picture of this galaxy where all the cold gas was in these orange little rings, that radiation heats up the gas. So I said before, all those orange little blobs, they are a reservoir for building future stars. So if I heat them up, they won't be able to form stars in the future. I think it's fine as there's nothing written at the top of the screen.
Okay. You managed to do it downstairs.
Yeah. Or I don't know, should I? I don't know. Should I just leave it?
Yes.
Oh, okay. I'll just say what's written at the top of the screen once. Okay. So basically, if all that cold gas now absorbs all this radiation, it will get warmer. So what would happen to all these little kind of cold gas rings here? The temperature would be increased. To form new stars, what I need to do is I need to collapse the gas. So I heat it up, it expands, and it will no longer form stars. So I can basically stop star formation in the galaxy if I make the gas hot enough. And that's kind of cool, right? Because I could affect the future of the galaxy.
I realised I could move you.
Oh, I don't think I need to. Oh, there I am again. Now you can read the top slide. Okay, so we learned that basically, if I have potentially star-forming gas, I might be able to stop that star forming because I just heat it up. But we can do cooler things, right? The other thing we can say is like, what does the black hole do in general to gas clouds in the galaxy? Now, I said before that the stars are basically so rare. So if you look out in the sky, like they don't really fill the volume, right? They're very, very rare. Most of space is empty. So that means most of the light can just go out. That gas clouds can kind of fill the volume more. So they're kind of basically bigger. Now, the other cool thing you could do with gas clouds in the galaxy is that if you have radiation, it has radiation pressure. So if you have radiation, it basically pushes on the material it's absorbed by, right? Because it basically it's quantum physics. No, it's basically in some way it is like a little particle that will basically kind of push against it, right? You're basically bombarding the material with kind of photons that are then absorbed by the material. So what that means, basically, if you throw enough light at something, you're kind of pushing it bit by bit. You have to throw a lot at it because, of course, you know, they're quite light, so you don't get a lot of push from a bit of light. Like I couldn't get a flashlight and I push that TV out of the window, right? I need quite a lot of radiation and quite a lot of exposure. But if you have gas clouds in the galaxy, it turns out that what you can do is you can basically push it out with the light. So through the radiation pushing on the material, I can basically start to move it out of the galaxy. Oh, now I need to click on this again, right? So this is much like something like a solar sail. So that's something we can use for space travel, where again, basically the light is absorbed, pushes the solar sail out. So we can basically accelerate gas clouds. But that is even better because, as before, as I said, that in the galaxy we need gas to form new stars. So if I push out gas, it can no longer form stars in the galaxies because it's gone. So what that means is that overall, I have two mechanisms here to basically affect how much stars are formed in the galaxy. And that is quite substantial because really how much stars a galaxy forms like means a lot for its properties. It also, of course, means a lot for its future because if it stops forming stars, it stays at the same mass. So it affects its mass overall. So this is quite a big impact on the galaxy. And it turns out those two mechanisms that I told you about, basically heating the gas and kind of pushing it out, together can cause what we call kind of outflows from the galaxy. So this, this is an artist's impression. It's an artist's impression of a galaxy. That's not a picture of a galaxy. But what you see here is kind of this rig-like thing here. That's the galaxy. That's kind of in gray. And then you see these purplish things kind of whiskey going out. And what that is showing is basically how, if the supermassive black hole in the very center is active, you can basically drive out the gas both by heating it and by pushing it out. And again, really affect the future of the galaxy. Okay, so maybe let's.
I asked a question.
Sure.
ESA is the European Space Agency.
Yeah. Yeah.
ATG.
I don't remember. I just took it from the credit from the image when I found it on the internet. Okay, so what I'm going to show you next. So basically what I told you is that if the black hole accretes through all that radiation, can affect the evolution of the galaxy. And what astronomers have learned over the last decades or so is that this is actually really, really important for understanding the evolution of galaxies overall. So that tiny, tiny bit of mass, we kind of need it to understand how galaxies evolve overall. So what I'm going to show you next is a cosmological simulation. There'll be quite a lot of happenings, so I'll warn you before. So what we're basically going to do here is we're going to try to see the whole evolution of the universe. So we're going to start from the beginning of the universe. Someone has simulated this all. And what you're going to see in the beginning is quite kind of a smooth distribution, so it's going to be quite fuzzy. And you're going to see how gravity starts to build galaxies. And then I'm going to point out when the black holes start happening and start affecting this. Again, this is a simulation. It's called Illustrious. And basically we start here, time since the Big Bang, you can monitor that here. So we basically start with kind of quite a smooth distribution. As you see here, what we start to see is kind of galaxies forming. So what's basically happening is that gravity starts to pull the material together and starts to form a number of galaxies here. These kind of nice little clumps here. This is taking its sweet time, right? So about 2 billion years are gone now, and it just keeps going, right? And so you keep seeing, and this is not actually rotating, it's just rotating to make it look better. You're going to see, as you go on, you're going to see, because now we're going to start to see the supermassive black holes, right? So what you have in these simulations is the supermassive black holes in there, and these effects that I just described to you, they're happening in this simulation. So you start to see these kind of red bubbles and these explosions, and that's the supermassive black holes, because that's the gas in the galaxies. And you see, like, once they start being active, it completely changes the structure of those galaxies. So we see all of those gas being blown out. And you keep seeing this kind of individual explosion, and that is basically as a supermassive black hole has accreted a bit of material and then starts to put all these energy out. And you see more and more explosions happening here. And what this is showing you is that if we take our physical understanding of this, of like how black holes accrete, how much energy they put out, we can really see that as kind of black holes start to accrete, they entirely change the properties of galaxies. They blow out all the gas. They can stop star formation. And nowadays, we really think that to understand galaxy evolution, we need to understand this process. We need to understand this energy input. And that's what this simulation shows as well. And you really see this massive impact as these explosions go off. And that, it starts from there. Oh, it's gone now. Yeah, we're done. We're now going back to the stars. We're done. This is the end of the universe now. No, this is now. It's not the end of the universe. It's just now. There we go. Galaxies to Mars, right? So basically that kind of really shows this massive impact something so small can have. And that is the amazing people who did this simulation. Okay, but that is simulations, right? So this is basically a bunch of physicists writing down equations and like putting them in a supercomputer. You can then ask yourself, well, are they making this up? Basically, all these massive explosions that I showed, all these outflows, are they making that up? And to that, I should say that we actually also see a lot of this in reality. So if we see galaxies with kind of these accreting supermassive black holes, we see a lot of these kind of fast outflows. So if we see at the center of the galaxy, very near the black hole, we can often see gas moving at about 10% the speed of light, which is very, very fast. So we can basically see gas here, and that's 30,000 kilometers per second. That's really quite fast. So if you're near the black hole, you can really see this being pushed up at very, very high speed. But not only that, if we move further out into the galaxy, we can still see these very, very extended kind of outflows, so basically kind of cones, and these kind of wispy purple things there. So that is basically kind of large scale, just gas moving away. And even quite far away from the galaxy, that can move at 10,000 kilometers per second. So we see all of those in galaxies, we see this happening. And 10,000 kilometers per second is fast. It is also fast enough to basically escape the galaxy. So the key here is that it's fast enough that basically it goes so fast that it just flies away and it will never come back, stopping star formation. So not only can we show in simulations that this really works, this has a massive impact on galaxy evolution, we also see these effects happening in galaxies everywhere. So that is that is kind of a cool thing for something so small in a way to do, right? Because when we started, we showed that these supermassive black holes, while they're individually quite massive, millions to a billion times the mass of the sun, they're still like a tiny, tiny fraction of the galaxy. But we just needed to feed them a little bit of gas, and they could have this massive impact on the galaxy overall. So that's kind of a wonderful thing. Yeah. And there's like one more thing, because I realized, so I wrote this talk and then I realized that there's one feature in here that's super exciting, but it didn't really fit in the main narrative, so I just added on one more thing, jets. So one more thing. So what we talked about here is this kind of accretion disk, so that's the material falling in, great stuff. You get all this radiation from it. One more thing that we have from these accreting supermassive black holes is what we call jets. So basically what we see here is you see the material going in a disk, but you also see perpendicular to that jets. So those are basically, they go out either direction, perpendicular to the disk as is shown here, and they are very kind of thin. So they're not kind of broad like we see in those outflows before, they're kind of very pointy basically. They're also quite fast, they move basically at the speed of light, so they're cool. So jets again, so we'll look at another galaxy here. So this is a galaxy we see side on. You see this kind of brown, gray, orangish kind of disk here. So that's our dust and gas in the disk of the galaxy. So we're basically seeing this disk etched on. But what we're also seeing here is these kind of two gigantic kind of blooms here coming out. And those are jets. So this is kind of this material ejected from the black hole that moves at about the speed of light. And as you can see here, it is absolutely massive. So it is really, really huge. It's much, much larger than the galaxy. So these jets also can have an impact because they basically carry all that energy out like far, far beyond the galaxy. So again, from that, we can really kind of change the way the galaxy evolves. We can change the future of that galaxy using the jets as well. So hopefully, by now I will have convinced you that supermassive black holes are very exciting and they really play a major role in how galaxies evolve. So despite the fact that they really don't matter for the gravity overall, once they accrete, they can really change how galaxies work. And I'll just leave this movie running because it looks nice. And once you see the explosions happening, you'll see the black holes. Thank you very much for listening.
Thanks for that. That was great. Yeah. At the beginning, you showed the Nobel Prize winners. Roger Penrose has lectured here.
Oh, cool! That's exciting.
At the time, it was before he'd been awarded the Nobel Prize, but the person who introduced him said that he did have it, and I was in the audience, I was seething that they should get something so wrong. But perhaps they were just looking at the future because he was awarded it shortly afterwards.
Maybe they knew something you didn't. I don't know.
Anyway, we'll take questions. We'll start off in the room, and then if those of you who are online could put questions in the chat channel, we'll get round to you afterwards. So I'll get the roving mic.
Turn on the lights.
I certainly use some more lights. I can't see. Right. Okay. Any questions in the room? Yeah. Right. I'll start there where I saw the first hand go up. Is that along here?
Just a couple of questions, if I could. One was related to, could you explain why and how black holes form? And the second question really was about, you mentioned about radiation,
Yeah.
and also jets being ejected perpendicular to the mass of the galaxy. I was just trying to get clear what frequency the radiation might be, and were you also talking on the jets about material, or is that also just radiation? Thank you.
So if I start with the first one, so how black holes form, that we know some options, but we don't know which is dominant. So one way you form black holes is you basically collapse a star. So you have a supernova, there's a black hole left over. Black holes left over from that are small, so they're like up to maybe 10-ish or so solar masses. So you need to, so the accretion also, of course, adds to the mass, but you need to accrete them fast. You really, really need to kind of break all kinds of limits of accretion physics to get them to high enough masses that we see them early in the universe. There's other ways to form more massive black holes. One of them is basically just to directly collapse into a black hole, or to kind of basically form heavier seeds, so heavier initial ones that then grow faster. But we don't really know which one is dominant. So that's kind of open research. But basically those few options, kind of direct collapse, you basically form some sort of a kind of stellar death, a black hole, and you just need to grow it fast. And for the jets, so the radiation from that, it's synchrotron radiation, so it is electrons and protons, and radiation. So mostly the jets you see in the radio. So most of those images of jets you see is radio emission. Some of them also, so they also emit at a very high energy, but mostly it's kind of synchrotron emission. So it's radio. So in radio wavelengths.
I just wanted to ask, is accretion a permanent state? Do all black holes accrete all of the time, or is this a process that is intermittent?
So it is intermittent. It is intermittent because most of the black holes we see are not accreting. So we think that it's about 1% of their lifetime they spend accreting. One of the reasons for that is that they basically run out of material. So a black hole, for a black hole to be like properly accreting, it might need up to kind of a solar mass a year. So at some point, if you basically feed it some gas, it will just run out of it, right? It will have eaten it all and then it's done. So you basically need an event to kind of feed gas into it. So they're not all accreting all the time. It's actually quite rare they are accreting. But we think that all of them during their lifetime will have undergone phases of accretion. It's just not all the time.
Thank you very much. It's extremely interesting. Can you comment on what we know about the chemistry of what's going on to the atoms in this situation? It strikes me that we sit here on Earth and we've got the periodic table and we've got a nice little row of atoms and we all know what they are and they have a certain number of protons and neutrons and electrons. But actually, in the environments that you've been describing of very high temperature, very high energy, do those atoms survive, or are we looking down at subatomic particles and gluons and quarks flying around individually? And if so, how do they all nicely realign and come back together to fit the periodic table that we know on Earth?
So So one of the things for astronomers is great because most of the universe is hydrogen or helium. So I'm in the physics department. They always make fun of us because for astronomer, everything else on hydrogen or helium is a metal, and so we kind of class everything else as just a general class of like weird materials. So generally, most material is hydrogen or helium. Anything carbon, oxygen, anything. Not to talk about uranium or whatever is extremely, extremely rare. So that means most of the material accreting will be hydrogen and helium.
A lot of it's iron. They've got in things like the sun and the Earth. The centre of Earth is iron. I just wondered whether these atoms have survived, like whether they break down, but under the huge pressures and heat. But I mean, I guess it's hard.
Once they're in the black hole, they're gone, right? Because once you're basically in the black hole, basically you lose all that information. It's just matter at that point. But like in the accretion, they will survive. So we see a lot of those. So we see signatures of different atoms near accretion disks. So we see kind of emission lines. There's magnesium, whatever. There's all kind of there. So you're not destroying the atoms as long as you don't go into the black hole, and then it's just all black hole. What now?
When you say it's just all black holes, any idea what that is?
So it's basically, I mean, this is.
You tell me when.
So basically, right, once you enter the black hole, kind of all information is lost. So then the only property a black hole has is mass, right? If I throw this into a black hole and whatever has the same mass as this, right? It basically all just adds to the mass of the black hole, right? Like all the information about what this was or what that laptop was would be gone, and all you're adding is like you're adding to the mass of the black hole. It just has a higher mass at that point because it can basically never be extracted anymore, but you're never returning this lectern or laptop or anything, right? You're just adding to the mass of the black hole.
Right, I'll take a couple more questions from the room and then we'll go to the chat channel.
Thank you. Thank you very much for an interesting lecture so far. What is the nature, if you feel able to explain it to us, of what you call energy of a black hole? Is it gravity or is it radiation of some form?
I'm not so the energy. So the black hole just has a mass, right? Which gives it a rest mass energy. I'm not sure I understand the question.
I better ask my question more clearly.
Yeah.
And I'm sorry.
No, that's okay.
I didn't manage. I wanted to know, in terms of basic physics.
Yeah.
I'm sure you know what I mean. What is the nature of the energy of a black hole? Is it gravitation or radiation?
I'm not sure. Yeah. Yeah, it has a rest mass energy.
Yeah. Okay. I'm going to go over there and then I'll go to the chat channel.
Thank you very much. It's a very interesting lecture. Thanks. Just a question on what you said earlier about the effect of the gravitation of the black hole on the rest of the galaxy. But is the implication of the fact that these jets are perpendicular, that the black hole is rotating in the same plane as the galaxy, and if so, why?
So this is a fun question. So the black hole has a spin. So it basically it contains the information of basically the angular momentum, so like the sense of the orientation of any material that went in. So whatever material, if the material that went in was doing that, it will basically have the same kind of spin. So if you have a black hole and you always feed it in a nice orderly fashion, like basically with the material from the disk, you're going to basically spin it up. So it's basically going to turn the same way as the galaxy. Basically, it's going to have the same kind of rotation. If you then do things like you merge the galaxy, or you basically merge it with other black holes, that's going to be messed up. So at that point, you're going to potentially have a different orientation. These jets, so they are either basically go with the rotation of the black hole, or they go basically with how the accreting material is aligned, so perpendicular with that. Not quite sure which is which. It's also really hard to tell. So the fact that those jets often, but not always, kind of go like that might either tell you that that's what accreting material is doing, or that's what the rotation of the black hole is aligned with, and we don't quite know. But because it's really, you can really measure the spin very well, so it's really, really hard. Yeah.
Okay, I'm going to the chat channel. There's a question from Gary about published work from the University of Hawaii. Gary, would you like to unmute and ask your question directly? Let's see if that works. If I don't hear anything, I'll read it out. Okay, he says, do you have any views on the recently published work from University of Hawaii that the gravitating mass of a black hole can increase with the expansion of the universe independently of accretion or mergers?
I read that paper. I read that paper. So I'm not sure. So basically that model. So they had a model that the black holes grow with the expansion of the universe. I'm not sure. I'm not convinced by this yet. I think one of the problems is that the measurements you need to basically test this model are very, very complex, because you basically need to go throughout the universe, you need to measure the black hole masses, and you need to basically see them grow over time. That is really, really hard to do. One of the main limitations is that to measure the mass of the black hole, you ideally want it to be accreting, then there's really neat ways to get the black hole mass. If you don't have accretion, which is most of the galaxies, it's really, really hard to get a black hole mass, and it's basically impossible outside the local universe. So basically the kind of data you need to test this model that Gary, I think, was describing, yes, is like extremely complex. And I think it's very difficult to do that reliably. So it is a model. I'm not sure if the data is here at the moment to really test it clearly.
Right. Next, we have Roger Moses. Now, Roger, you start off by saying we don't have a supermassive black hole in the Milky Way, but I thought you said that we did.
We do, yeah.
So I think the answer to that first part of your question is yes, we do have one, and
yes, we do.
And you said that nearly all galaxies, virtually all galaxies, do. And then he adds a comment. We know that atoms up to uranium arrive at the Earth with high relativistic velocities in the primary cosmic rays. Roger Moses did some research in the cosmic ray, detecting cosmic rays. So that's why he has an interest in that. But I suppose, I mean, these jets and so on you said are mostly hydrogen and helium.
No, the overall gas is hydrogen and helium. Yeah. So cosmic rays, I don't know much about cosmic rays. And I know it's really tough work, and it's really difficult to figure out where they're coming from. So I don't really know what, like, if I'm not sure if the question is if the jets would be related, would be kind of trace, would be causing cosmic rays. So.
And Hugh Allen, this is the last of the chat channel questions for the moment. Hugh Allen says, he asks, what's the implication for life in a galaxy with an accreting black hole?
Cool. So that's a fun question. So there was actually a paper a few years ago where they tried to do that, because, I mean, I kept showing all these pictures where, like this one here, where you see like this really, really bright core. So it is a bit complicated. So for the Milky Way itself, lucky for us, we are kind of in the disk of a galaxy. So basically, if the black hole in the center of the Milky Way were to start accreting at quite a high rate, you basically see something very bright there. The question then is like, how much of that gets absorbed on the way towards us? If you're in a galaxy like the Milky Way, you're quite well protected by the disk because it's really, really, really dense, and a lot of the radiation actually does get absorbed. If you are much closer, possibly wouldn't be so good. So I remember that paper I think that paper concluded we'd be fine. It depends a bit where you are in the galaxy. If you're very close, so a lot of the radiation from that is very, very high energy. So that's obviously not great for life. But it really depends where you are in the galaxies. And I think we'd be fine.
Getting quite a lot of questions.
Should I still go ahead?
Yes.
Okay, thanks.
Hello.
Hello.
Very interesting because where I come from, our philosophy is summed up in Trimurti. Trimurti is three representations. One is Brahma, the creator, the other is Vishnu, the preserver, and the third is Shiv, the destroyer.
Mm-hmm.
And that Trimurti represents existence. And Vishnu, who's the preserver, has a finger pointing upwards, and on the finger is a spinning top with a spindle in the middle and the galaxy around it. And he's the preserver. So basically, what you've just been talking about, the galaxies representing the continuation of existence, he's the preserver. So it goes on. So, I mean, there's also an implication that existence is cyclical, because everything has a core around which I'm making a comment as to the summary of what we just heard today and how it's represented in the Trimurti from where I come from. And the question, implied question is, what are your thoughts on the cyclical nature? Do you think existence or the formation of the galaxies is cyclical, and will there be an end before there's a beginning, or do you think it's just forever?
So I mean, so the universe when you saw the simulation, the universe actually evolves quite a lot, right? In the early universe, there was lots of gas around, right? There weren't any stars yet. So there's been a massive evolution of the universe, and also galaxies like overall change a lot. The boring galaxies I showed you basically didn't exist at the beginning of the universe. They're starting to dominate now. So the universe as a whole isn't really cyclical. It's just basically going to a more boring place. So it's one of the things for astronomers, like the early universe is way cooler because like all kind of things were happening. There was all star formation. There were like, it was just a cooler place. Whereas now it's kind of, we're mellowing down. So I don't think the universe doesn't appear to be that cyclical. It's just calming down. Yeah.
Okay. Hi, thanks for the talk today. Forgive me, these two aren't related, but I just wanted to ask. So we've talked about radiation from the accretion disk and radiation from the jets.
Yeah.
Are either of those what we would call Hawking radiation, or is that something else? No,
that's something else. So Hawking radiation, you get without the accretion, so all black holes will emit Hawking radiation. So technically they will kind of very slowly evaporate. The thing is with these kind of black holes, so while they emit Hawking radiation, it is like beyond negligible, right, in terms of any other radiation around. So it exists, it definitely exists. It matters for smaller mass black holes. For those, I think you possibly could barely detect it. And it certainly would be like not even near as bright as any of the other processes. Yeah, but Hawking radiation is something entirely different. So for like people studying this, we just ignore it because basically it doesn't matter for our purposes.
Hi there. Is there a difference between supermassive black holes and ordinary black holes? And can an ordinary black hole become a supermassive black hole?
Yeah, so the difference is mostly that we kind of draw a somewhat arbitrary boundary at some mass. So there's stellar mass black holes which are I don't know, a few times the mass of the sun. Then they're kind of intermediate mass black holes, which are maybe 100 or 1,000, and you would start calling something supermassive and like 1 million or so of the mass of the sun. There is possibly kind of a reason to keep them separate, right? Because so stellar mass black holes exist throughout galaxies, because they basically, when basically massive stars end their lives, makes a black hole. So in a galaxy like that, there will be black holes sprinkled all around. For the supermassive black holes, we kind of have them to be central to the galaxy, and they're generally, unless you recently had a merger, they're to be one, right? So it's kind of unique to the galaxy. So in that sense, they are kind of different. But to get to the supermassive black hole, you kind of have to kind of grow smaller black holes. So there must be some kind of continuum where smaller black holes start to grow into bigger black holes.
You've kind of touched on my question there, which was, why is there only one into each galaxy? And why is it at the center?
So why there's only one? I don't actually know. That's a good question. So if you had to, this possibly kind of touches down to that, where there's some kind of a continuum, right? So what happens if you basically place a kind of massive object in the galaxy is it will kind of sink to the center of the gravitational potential. So if you set up a simulation and you place the black hole kind of sideways, over time it will basically kind of fall to the center. So if you have something relatively massive, it will at some point be at the center of the galaxy. Once it's at the center of the galaxy, it will, if you had two black holes, somehow you ended up with two black holes, they will eventually merge and form one black hole. So there's all kind of processes that kind of like put everything big to the center, and then it will merge into one. It's a more complicated question, because one thing you could ask, well, why is there not 5 that are on their way down? So, and we don't really know that. That kind of comes back to like, how were they formed exactly? And like, how are they, how are they migrating to the center?
Thanks again for a great talk. You had some in the animations, galaxies merging and the black holes merging. When black holes merge like that, would there be a lot of gravitation radiation emitted, and would that be detected by today's gravitational wave detectors?
So you get gravitational waves from that. So you might have heard about the kind of LIGO detection of basically neutron star black hole star mergers. So the supermassive black hole mergers would emit basically the same radiation, but they are at a different frequency, because they're basically much more massive. So the gravitational wave detectors we have right now are quite small. So I'm not sure, how long are they now? 1.2 kilometers or something like that, right? So their arms are that length. So they then basically detect waves that are kind of comparable to the length of their arms. The waves from the supermassive black holes would be basically larger, so you need longer arms. So there is a planned gravitational wave detectors to go into space, because you basically need like millions of kilometers long arms or so. I forgot now where exactly they are, but that is meant to detect supermassive black hole mergers. And that's going to be kind of possibly that question about like, why are there not more black holes? That's going to really tell us like how many mergers there are. So hopefully in the future we will get detections of those, and it'll be great. Not right now, because LIGO has the wrong arm length.
Right, I'm seeing if there's anyone who hasn't asked a question yet. You could be next.
Yeah, sure, that's it. I like the fact you doubted the Hawaii University, was it, theory, because you couldn't measure it. So to what extent is everything you've described supported by theoretical physics and mathematics?
So it's a mixture. So I mean, what we can say, so we know there's accretion disk, right? We can absolutely see them. We can test the physics of that quite well. We can definitely see all those outflows, right? We can measure that. That's kind of well understood. So what we are very good at as astronomers is going to an individual object and kind of pointing out what it does. You can go to this one and say, oh, the gas is moving at like 1,000 light years away. It's going out at 1,000 kilometers per second, and it's a mass outflow rate of 10 solar masses per year, whatever. That's kind of easy to do. So you can do that. So you can go to this one here, and you can say what it is. So you can say that also from the theory. So we understand quite a lot of the basic theory quite well. It of course gets very complicated because it's quite messy physics. So the details are difficult. The bit that's really hardest to do is galaxy evolution, because if I want to see, like, this one has an accreting black hole, and I say like, wow, I want to know what it does to the star formation like half a gigayear from now. I can't do that because I can't hang around for this, right? Like I can't wait for that long time. So what we have to do is we basically try to look at the universe, and because the further away we look, the further back in time we look, we could kind of take those galaxies and say, well, these must evolve into these, so we can do some statistical analysis. And that's hard. That's really, really hard, right? And so I think that a lot of this like longer term evolution, we have a basic understanding of it, but the details are really quite complicated. So I think that there's a lot of observations that support all of the things I said. For all of those, there's also bits where we're like, we don't quite know yet how that works, because it's difficult, it's quite tricky.
You may have answered this already, but can there be black holes that are not connected with galaxies, just in empty space?
So there could be, and we don't know if there are. So one way to get a black hole not with the galaxy is if you're going to merge two of them, that there's certain ways, or if you're going to merge two or three, there's certain ways to, like, if they don't quite merge, you basically give one a kick and you just throw it out of the galaxy. So you can do calculations where you say, for some galaxy mergers, you should basically just eject the black hole and it should be gone. That's cool. The problem with that is that would be really hard to see, right? Because at that point, what you would have is you would have a black hole floating in space, nothing around it, so it's not going to accrete, nothing around it to have a gravitational influence on it, it would just be there. So they can exist. I think it will be very, very hard to prove that they do, because the observations of them can be very hard. But some of them should exist. But it's difficult to determine where they are.
Okay, so a question I'd like to ask is, when gas is expelled from a galaxy, is it effectively lost into intergalactic space forever, or can it eventually get sucked back into another galaxy?
So it can. So one of the things I've kind of ignored here is because so if you see those galaxies, that's quite neat, right? And you see the gas in the stars, but there's actually a lot of gas on like much larger scale. So you basically have like a large halo of gas around it that's heated at quite high temperature. So what we think broadly happens is that you basically like add it to this large reservoir of hot gas around the galaxy. So I said it would be gone, right? But it will still be, of course, somewhere in the universe. So one of the things that happens with this like large halo, so this basically large ball of hot gas around the galaxies, that at some point that does cool, so it just cools down, at which point it will fall back onto the galaxy. So while I said it's gone forever, we also know that basically you have some amount of recycling of the gas back onto the galaxy. So it's possibly not gone entirely forever, possibly for a while. But we do see quite a lot of inflow of gas from those larger scales as well.
Right. Any more questions in the room? Let's check the chat. So I think we've come to an end then. So I've learned a lot this evening about how supermassive black holes do and do not influence the galaxies that they're in, which I didn't know before. So I'm very pleased to learn all that. And it's just been a remarkable tour through the effects of supermassive black holes on galaxy evolution. Absolutely fantastic. So let's put our hands together for